Let's begin chapter 2, where we're looking at basic structures like sets, functions, and matrices. So we'll study them in some detail. There will be some connections with logic we'll see as well. Section 2.1, sets. So what is a set? Well, yeah, it's kind of hard to say exactly what it is, but for us, for now, we can say it's a collection of objects. All right, but I'm not telling you what an object is. But we need to get used to their terminology and notation. Okay, so on one level, sets are very simple. Yeah, you can think of objects like numbers. Example 1. So we're saying S is equal to this collection, 1, 2, and 4, these numbers. All right, so this S is a simple set with 3 elements. And we write it like this, so these braces on each side and separate the elements with commas. All right, so yeah, it's a very precise notation, so make sure you get that right. More notation, well, you have 4 is in here, so 4 is an element of S, and we use this symbol like an E to mean is an element of. Yeah, the number 3, that's not in there, so 3 is not an element of S. All right, also 0, 5.6, so any number that's not one of these 3 is not an element of S. So to make a set, yeah, we just need to know exactly what's in the set. So what are the elements that it contains? And it doesn't matter how you order the elements. So the set 1, 2, 4, that's the same as the set 2, 4, 1. And it doesn't matter how often you list the elements, they only get counted once, really. So 1 is in this set, 2 is in this set, 4 is in this set. So this idea of cardinality, so that's how many distinct elements a set has. Okay, so you just count them up. And we use this notation, 2 vertical lines. Yeah, it looks a bit like an absolute value, but for a set, it just means how many distinct elements. All right, so the cardinality, it'll be 0, 1, 2, 3. So any non-negative integer. Or we'll see infinite sets, so the cardinality could be infinity. So for this set S, the cardinality is 3. It has three distinct elements. Here's a bigger set, we'll call it T. So T has 2, 3, 4, 5, 6, and 7 as elements. Count those up. There are 6 different numbers. So the cardinality of T is 6. The simplest way to write a set is just to list everything in the set. We could have also written this set as 2, 3, dot dot dot, 7. So if it's clear that you mean just continue 4, 5, 6 until you get to 7. So that's another way we could have written this set. So these ellipses are useful when if you have a lot of elements, dot dot dot. But another way, an important way, is this set builder notation. Okay, so we can describe these as integers between 2 and 7. Okay, so in set builder notation, we could write that T is equal to all x's such that x is an integer and 2 is less than or equal to x, less than or equal to 7. This line is part of the set builder notation. It just means x's with these conditions. Alright, so different ways to describe sets. Here are some common sets. So the simplest set is the empty set, so no elements. It has this symbol, like an O with a line through it. It's like a Greek letter phi. Or you could just use this symbol, braces with nothing inside. The cardinality of the empty set is 0, so no elements. Here's a bigger set, Z, capital Z or a bold Z means the set of all integers. Okay, so all the positive and negative integers and 0. And that's certainly an infinite set. Why is it called Z? Z is the Zahlen is the German for integers, so it's from the German. Z plus, that usually means the positive integers, so 1, 2, 3, 4, and so on. Q, that's the rational numbers, so all the fractions. So that's a good example of set builder notation. So the rational numbers, it's every p over q such that p and q are integers, and also q is not equal to 0. Alright, so so all these numbers, those are the rational numbers, that's q. The real numbers, that's R. Okay, so everything on the number line. So that includes the rationals, but also more numbers. So all the decimals, including infinite decimals. That's the real numbers. And then the complex numbers, those are numbers of the form a plus bi, where I is the square root of -1, and a and b are real numbers. All right, so we have these famous sets of numbers. So these are good examples of sets. Do sets have to be made out of numbers? No. No, it's a very kind of general concept. And so the elements of a set could be anything. They could even be other sets. Example 3, let U equal this list. So we have the empty set. We have Japan, so a country. We have the set of integers, and we have this set of A, B, and C. There's 3 letters. All right, and this makes sense. So U is a set because we know exactly what's in there. How many elements, distinct elements, does U have? Well, it has 4. It has 4 elements. 1, 2, 3, 4. All right, so even though the empty set, it's empty, but the empty set is an object. We have a country. We have all the integers, but that's a single set. So we treat that as one element. And then this set, okay, it has 3 elements inside it, but again, the set itself is a single element here. Okay, yeah, so when you start thinking about sets containing sets, then you can see this idea could get more complicated if we let it. All right, next idea, subsets. Definition, a set A is a subset of set B if all the elements of A are also elements of B. And we have this special notation. So this is subset notation. So it's like a C with an extra line underneath. So this means A is a subset of B. Let's take S equals 1, 2, 4 again. Then 1, 4 is a subset of S. Okay, so the elements of this set are all elements of S. But this set is not a subset of S. Yeah, I can see these 0 and 3 are not in S, so this is not a subset. So in notation, we can write that like this. So 1, 4 is a subset of S, but this guy is not a subset, so just strike a line through it. So that means not a subset. Yeah, one case, every set is a subset of itself. Check the definition. So are all the elements of S also elements of S? Yeah, that's true. So every element is a subset of itself. Okay, also the empty set is a subset of every set. So the empty set is a subset of S. That's a bit stranger. Let's check the definition. So is it true that all elements of the empty set are also elements of S? Well, the empty set doesn't have any elements, so there's nothing really to check, or nothing goes wrong. So there's no elements of the empty set that are not in S. All right, so yeah, we can just remember the empty set is a subset of every set. The next definition, so related to that, so a set A is a proper subset of B if it's a subset and not equal to B. And then so we use the same notation but without the line at the bottom. Okay, so with the line that's subset, but without the line that's proper subset. So we're not allowing equality. So yes, very similar to greater than or equal to. All right, so subsets, we have this notation, and proper subsets, it's the same thing, we're just not allowing the sets to be equal. Yeah, our notation's building up, and yet this can get confusing, so we have this symbol is an element of, this means proper subset, this means subset. And here's a connection to logic. Statements like X is an element of A, or A is a proper subset of B, or A is a subset of B. So if these statements make sense, they should be true or false. So only two options. Again, just like less than or greater than. All right, so let's see an example. I'm using this notation correctly. The same S. Decide if these statements are true, false, or don't make sense. Part A, 4 is an element of S. Well, that makes sense. And it's also true. Yeah, so 4 is in here. So this is true. Part B, now here we have a set containing just 4. So this set containing 4 is a subset of S. That's true. So all the elements of this set are contained in S. So this is true. How about this one? 2 is a proper subset of S. Well, this is similar to B, but the difference is there are no braces. So in fact, this doesn't make sense because 2 is not a set. 2 is just the number 2. if it had braces around it, it would be a set containing 2, but this is just a number. It's not a set. So for this proper subset notation, we need to be comparing 2 sets. Okay, so this does not make sense. It's because we're not comparing 2 sets here. 2 is not a set. How about D? All right, so here's a set containing 1 and 2. So is that set an element of S? Well, I see the numbers 1 and 2 here, but this whole thing is one object. This object is not an element of S. All right, I hope you can see that. So this one object, this set, is not in here. So this is false. All right, so the set containing 1 and 2 is not in this list. So it's not an element of S. Okay, one last one. This is saying 1 is not an element of S. Well, 1 is an element of S. So this is false. If it was 1 is an element of S, that would be true, but not an element is false. All right, so the moral is, yeah, just be careful. Make sure you're comparing sets when you use the subset notation. Okay, I think that's just what I said. Okay, maybe let's take a look in the book. Okay, sets, examples of sets. Yeah, this example has letters as elements. The set V here is the set of all vowels. Some odd integers. Yeah, here's an example of a set. Yeah, all the numbers between integers between 1 and 99. Yeah, you don't want to list them all, so you can use ... instead. And set builder notation. Yeah, there's one other set here, n. The natural numbers, although it's confusing. Some n's include 0, some n's don't include 0. In number theory, they don't include 0, but in logic they do. So be careful when you see an n. Yeah, here are some important sets of real numbers. This interval notation. All right, so the interval, so we're looking at real numbers on the number line. Okay, so with square brackets, that means all the real numbers x between a and b, and including a and b. So that's all of these numbers. Okay, so square brackets means you're including the endpoints, but round parentheses mean you're not including. So this round parenthesis here means I'm not including the number b, but everything up to b. Here this starts, so this one means all the real numbers between a and b, not including a, but including b. And the last version, if you have two parentheses, well, if it's interval notation, it means all the real numbers between a and b, not including a and not including b. Okay, so yeah, we'll be using this notation in later sections. Yeah, did I forget to mention this? So two sets are equal if they have the same elements. And yeah, it doesn't matter how you order them or if you list the elements more than once, it's still the same set. Yeah, here's George Cantor. He has a famous set named after him. The empty set. Yeah, as we are starting to see, sets can get very complicated. If sets get too big, then Bertrand Russell, a famous mathematician, philosopher, found that there are problems. Yeah, we'll come to Venn diagrams, subsets. Here's Mr. Russell. And proper subsets. Mr. Venn. Okay, let's go back to the notes. Yeah, so power sets next. So if A is a set, then the power set of A has this notation, P of A. And what does it mean? It means the set of all subsets of A. Alright, so think of all the smaller sets that are contained in A, but also so A is a subset of itself, so that's in there. So all the subsets from A down to the empty set. And so the power set can get pretty big. Example 6, find the power set of this set S. Alright, so we know S is a subset of itself. We know the empty set is a subset of any set. And then we have the smaller sets in between. So if you make a set just containing 1, that's a subset. Just containing 2 or 4, those are called singleton sets, just containing 1 element. And there are 3 more. The set containing 1 and 2 is a subset. 1 and 4, 2 and 4. How about 2, 1? Is that a new subset? No, so this is the same as 1, 2, so we don't count that again. So yeah, the order doesn't matter. Alright, so I can't see any more, so it looks like the power set of this S has 8 elements. Okay, and the elements are all sets themselves. So we can say the cardinality of the power set of S is 8. Example 7, suppose a set A has only one element, X. Find the power set of A. Alright, so if A is a singleton just with one element X, and then we have the empty set, we have A itself, and yeah, there were no more subsets, so the power set of this A just has two elements. Right, so yeah, the empty set, that's always in the power set, and the set itself is in the power set. And notice I'm using the element notation here, and that's the correct notation we need here. We're not talking about subsets, we're talking about elements, because the elements are subsets. Alright, so these Venn diagrams that we saw in the book, invented by John Venn. Yeah, so these are a useful way to picture sets. Yeah, it's always good to have pictures. So that's set T from example 2 with containing the numbers 2, 3, 4, 5, 6, and 7. Yeah, if we wanted to kind of put it in context, we could think of it sitting inside the positive integers, z plus. And you can make a picture. So the rectangle represents so all the positive integers, and then we can see t sitting in there, the numbers 2, 3, 4, 5, 6, and 7, and the other positive integers are outside the circle. Okay, so the usual way is to write the universal set, so that the whole universe we're thinking about, in this case the positive integers, that's a rectangle. And inside that you have smaller sets. So this other set S we've been looking at, you can see how it relates to T. Yeah, so here's T and here's S. And we can see a S is not a subset of T. It has this extra 1. And T is not a subset of S either. So Venn diagrams, they're a good way to see, to look at sets and see how they're related, different sets. And we'll use this in the next section. And the last topic, Cartesian products. So this is a way to multiply two sets. Yeah, we're just multiplying two sets here. First, we need more notation. So if you see two things not between braces, this time between parentheses. Well, in this context, it means that means an ordered pair of two elements, A and B. Okay, so if it was braces, it would be a set, but the parentheses mean it's an ordered pair. For example, here's the ordered pair 1, 2, and it's ordered. That means that's different from 2, 1. Okay, so the order makes a difference here. If you were talking about a set 1, 2, then the order does not make a difference. That is equal to the set 2, 1. And yeah, this also looks like interval notation, but no, we're talking about ordered pairs here. Okay, we get to the definition. So the Cartesian product of two sets A and B has this notation, A cross B. Yeah, it looks like multiplication. But what does it mean? It means the set of all ordered pairs A comma B in parentheses, where this little a is in the first set, capital A, and little b is in the second set, capital B. Alright, so we're making a new set, and it contains these ordered pairs. Okay, we'll see why that's very useful. But here's an example, example 8. Let A be the set 0, 3, and B be the set 4, y. Find the Cartesian product, A cross B. Alright, so we're making ordered pairs, and so all you have to remember is that the first guy has to come from the first set, and the second guy has to come from the second set. So the first elements are 0 or 3, the second elements are 4 or y. So we get these four combinations. So if we take a 0 and a 4, we get this ordered pair. Or we could take a 0 and a y. The other options start with a 3, so 3, 4, and 3, y. Okay, so this Cartesian product, it contains 4 elements, and each element is an ordered pair. And as usual, they're separated by commas, and we have the braces around them. Alright, so that's a Cartesian product. And one last example here, let S be the set 1, 2, 4. Let V be the set just containing Japan. Alright, so just to emphasize, these sets can be anything. And find these 3 Cartesian products. So first, S cross V. Alright, so now the ordered pairs have to contain the first element from S and the second element from V. Yeah, there's only one element in V, so the second elements are all going to be Japan, and the first elements are 1, 2, and 4. The other way around, so V cross S as the element from V first. Okay, so just switching the order. And V cross V, well, so that's ordered pairs where the first thing comes from V and the second thing comes from V. there's only one thing in V Japan, so we only get one ordered pair in this case. Alright, yeah, so just emphasizing, make sure you're using the parentheses and the braces correctly and putting in all the commas. Alright, so so it's the same here, so Cartesian products, named after this guy, Rene Descartes. Okay, so one more example. So here A is 1, 2, B is A, B, C, and the Cartesian products. Okay, so we're making these pairs. And so the first thing has to come from A, so it's either 1 or 2. And the second element of the ordered pair has to come from B, so it's A, B, C, A, B, C. Okay, so we get six ordered pairs in this example. And this is similar if you switch. So B cross A has the elements of B first. And there is a way to combine, so the Cartesian products of more than 2 sets, you just need, instead of ordered pairs, it's ordered n-tuples. Yeah, we'll come back to that. Okay, so that's our introduction to sets and all their notation.